Hello, it's Ryan. Welcome back. We're going to do some demos on permanent magnets and their fields, and one small demo on a current carrying wire and its field. Anyway, what you're looking at now are my hands and, of course, a compass. This compass is pointed due to Earth's magnetic field, which is about half a Gauss. And as you can see, the white pole of this compass is pointed to the north and the red pole is pointed to the south. So we'll use this every now and then in order to figure out what pole of a magnet that we're looking at, but that's a standard compass. If you see here, we have a bar magnet, and that bar magnet has a north and a south pole, of which I don't really know which is which yet. But I can figure that out. If I take the compass and put it near the blue side, it looks like the white part of the compass is pointed toward the blue side and the white part of the compass pointed north. So that must be a north pole. And of course, then this would be the south pole of our magnet. So I have a few magnets to show you. This is a standard bar magnet. We'll look at its field soon. I also have something called a cow magnet right here. This is a cow magnet. Have you heard of it? They're called cow magnets because they are actually given to cows. The cows are made to swallow these so that it sits in the first compartment of their stomach, of which they have 4 compartments. And then when they're eating grass and things in the fields, if any metal ends up in the grass that they're eating, it will get stuck to this magnet and sit in their first stomach, while the rest of the nutrients can get digested by the other 3 stomachs. Anyway, this is a cow magnet, but it's basically a standard bar magnet as well. Oh, there you go. This must be the north pole of the cow magnet because it attracted the south pole of the bar magnet. We'll look at both of those fields. I also have a very large horseshoe magnet, which I had to separate from all the other things so that it wouldn't affect them. But right here is our large horseshoe magnet, and we'll definitely look at the field for that. Now, one of the most interesting aspects, of course, of magnetic fields and magnetic forces is that they are an action at a distance force. And so if I take these 2 paper clips, I can bring the magnet near the paper clip, and the magnetic force will reach out and pull the paper clip toward it. Now, paper clips are interesting. They're called ferromagnetic, which means they'll extend the magnetic field of that cow magnet, and we can see it will attract the other paper clip. That's a magnetic force, and as you can see, it was an action at a distance force because it didn't need to be in contact initially. Now, I could take, just to kind of show you the power of that horseshoe magnet, there's a bucket of nails. We can see that if I take the bar magnet and touch the nails, I get some of those nails to be attracted to the magnet. They must be ferromagnetic. If I take the cow magnet, you can see it attracts a similar amount of nails, maybe a few more. But if I take that horseshoe magnet and bring it near, you can really see the power of the horseshoe magnet. This will attract most of the nails inside of that bucket. Now, this is a really powerful magnet right here. And actually, it's kind of neat. Those nails, if you can tell, they're actually kind of taking the shape of the magnetic field produced by this magnet. We know inside of here, if you look, all those nails are straight across, and we know the field lines between there should be going straight between the poles, and they should arc and form closed loops around the top. And look, the nails really do kind of form a nice arc. So these are kind of simulating the field of that horseshoe magnet.